Hello everyone. In this video, I will try to compare between the two previous antennas we have designed. One of them was a slot-fed patch antenna, and the other was coaxial-fed patch antenna. So in both examples, I maintain the same stack of the antenna, like the same substrate height and the same material, and I do just different feeding. So first we designed the coaxial fed patch antenna, and this is the dimensions somehow, and this is the feeding location. And for the slot fed patch antenna, we do like this. We have a slot on the ground layer, and then we have a transmission line on the back layer or in the bottom substrate here. So yeah, and here's the dimensions. And the main goal is to compare the performance, like in terms of radiation pattern. And in addition, I will show just how to explore CST results to see the far field, how to do some tricks to normalize the axes and so on, based on what we want to see. So just to give an idea, this was the two antennas we have designed before. We targeted something like 10 gigahertz, and then it is not exactly the same. So I did the normalization of the axes to align both at like I divide by the center frequency for each plot to just see the bandwidths, how it looks like, and so on like this. And it is clear that because of the antenna is the same size, the antenna itself, so most probably the bandwidths are the same. You know, it's like there's some theories called Boot-Fano limit, means that for a specific antenna or specific resonator or something, if you want to match it, you are limited by the gain bandwidth product. Means that here, for example, if you look at the 10 dB bandwidth, it's almost the same. The slight difference here because of the peak here is lower. So if you want to make it wider, you have to mismatch it. So the more you mismatch, the more wide you can get. So it's something like if you want to consider, you can mismatch a little bit, something to be here. So you will see that the line width will be wider, but most probably the 10 dB, it will not, like you will not really notice something very big. It was some formula to do this, to compare, but I can show it later if someone is interested. So this is just the idea, what we gonna do in this video, and let's go to the CST then. Okay, guys. Uh, First, this is the two antennas we have. So this is the slot-fed patch antenna. Here's the transmission line. Here's the waveguide port. And if you remember, like in the slot-fed, we couple by the H field, like the magnetic field, and it is maximum closer to the center and weaker closer to the edge. And for the coaxial feeding, it is something like somehow E-coupling or electric. So it is the vias here we feed vertically. So here's a little bit different because since we couple by the E field, electric field, so it is maximum on the edges and very weak nearer to the center. Means that in both examples we feed, and because we target almost the same impedance of the patch, so here is weak coupling somehow around the center, and here is weak coupling also, but around the edge, because this is the magnetic field coupling. So if you want to do the results, we go to the simulation field monitor. It open this window, so you can have a couple of parameters. In our case, we want the far field or even the E field, but we target the far field to see the radiation pattern and so on. So here, and you can either do many frequencies, or you can just target one frequency or something like this. It's up to you. And in my case, I have this antenna is 9.95. So this is what I want to do. Field monitor, and then far field frequency 9.95, and then press OK. Of course, yeah, I don't see it. So let me see. So this window will show, and then we have E field, H field, far field, and here you can do the frequency or decide number of samples between some frequency window or something. So here I can just target like this. I want 9.95 and then press OK. But in my case, I have it here. Okay, so here we go. And then we just press run. It can give you the option. I'm not sure if it will give here or no, but yeah, it gives you the option to restart the mesh, or you can just do only the results, because if I do restart, it will start meshing and solving and doing the result. And if I do continuous, like I used the thing before, and they'll just execute only the results, so it will be faster. Okay, so here we go, and we'll do the same for the other one, but here the resonance frequency was around here, so this is what I selected here, and here we go. And then we can press start, and then we can see the results. Okay. So one thing, if you want to also here you can create folder like how I did here. I did comparison and compare the field patterns and so on. So you can whatever name it, anything. Okay, and then you can just copy between the files. So for example, here I can go to somewhere, anything. I can take the zip router, for example, Control C, and then I go to the other file, and then I copy here, just in the navigation tree, copy here, or I can copy here somewhere. So yeah, so let's first look at the far field results. So we have here the far field. You go to the tab of the far field. You can have the option to have 3D field like this. If you press space, it fits the screen. Okay, and then you can either make the field transparent or no. This is actually nice for better visual experience. Okay, and then you can have structure transparent, like you will show the structure or no. So you can show the structure. I prefer this. And then actually like the structure transparent or no, so you can make the structure solid and then show structure even or no. Okay. And this is 2D. I'm not sure if it's working here or not, but okay, like 2D, like give 2D plot for theta and phi. It gave you the magnitude as a color plot, so I'm not sure why it's not working here, but Cartesian, oh, actually it worked. It worked, but anyway, it's not so interesting yet. And this also, like, I will not do it. Like, it's not the conventional way to look at the pattern. So here we can do the polar plot. So in the polar plot, you have a couple of options. Directivity, gain, realized gain, E field, E pattern, H field, power flow. Most probably all of them, almost they will give the same pattern. You know, if you normalize in dBs, it will be the same. Directivity is something like they don't consider any losses, any matching thing. It gave you like as if the antenna was perfectly matched and no losses. This is the maximum gain you can get. And then if you have some loss in the material, you can look at the gain, give you the gain or the directivity without, or like just calculating the efficiency of the antenna, and the efficiency which comes from the loss of the materials. And then the realized gain is basically the amount considering even the matching. So for example, supposedly if you have this gain and you have antenna minus 10 dB and minus 6, they will have the same gain. But if you do the realized gain, it will not really be the same. It means that the realized gain will be exactly like the gain if the matching is very good, like something like minus 20 dB or something. Okay, so here in this case, no difference between both directivity and gain somehow. Realized gain can be a little bit different because of the matching, but still, if we have no loss, no sense of this. Okay, so I will just compare by the directivity, and we can do this for both. So then we can also see that we have here either to have the magnitude or the absolute, and then we can have theta component, and then we can have here the angle we are sweeping with and the constant angle. So here we do the constant phi, and we change with theta. Okay, and here we can have cut angle based on the plane we want to look at. I will explain it in the whiteboard in a second. So usually if we have the antenna lined here in the Y, along the Y, and the antenna is aligned along the Y, and so it's like the conventional definition of the theta and phi and so on, okay? But so this theta means that the A theta component and phi is the E phi component. And here is the phase, and here is the phase. Here give you the ratio to show you the like the axial ratio and so on, something like it. Compare the two components. It's useful when you have dual pole thing and so on. Okay, so we can look maybe later on this as well. But here is the parameter so far. And yeah, here we go. So this is one thing. And another thing, if I want to scale the axes, so I copied first the two S parameters here. So what I can do, I go to the post-processing results template, and then to open me this window, I go to general 1D, and I add from this window 0D or 1D. Okay. This it opened for me another window. You can have the results which should get you something like just a number, or it can get you a curve, a graph or plot. So most probably I will do one, so I will scale the axis, and then I can divide by whatever the number I want. This is what I did in here. I divide by the center frequency I want, and decide here. I go to you'll see exactly the navigation tree, and you can go to whatever you want, comparison, you get the parameter, and then you divide the axis, and then you can have a variety of functions, and then you have to look at this to see what you want to do. Okay, and then whatever you finish, you press evaluate for both. Okay. So here we can look at the results for a while. I did everything. So at the beginning, you can see that for the coaxial cable, if you do the 4 planes, 2 things are high, 2 things are low. This is something we call it co-component and cross component, or like copolarization and cross polarization. Okay, so it depends on the plane you want to look at. Okay, and then if you want linear antenna, these small components, the smaller the better. Okay, so if you want to have a look at it, it is something like this for the patch antenna, like how the patch antenna radiates. Okay, so if the patch antenna is like this, and this is the radiating edges, like here, the patch like this, and then it flipped the field, okay, and then goes like this, and then the fringe like this, and then at some point do like this, okay, okay, and this is the far field, like, and then in the far field, this is going like this. It means that, rule of thumb, if the antenna or the linear antenna, like dipole, something that the current is like this. So if the current is like this on the surface, so the field is parallel like this, okay? Means that if, as in my example, I have here y, and I can have here x, and I have here z, okay? And also, maybe you know, or to just remind us, here is the phi, and here is theta. This like angle with z-axis, and this angle with x-axis. Okay. Okay. Means that in our example, we have the field is exactly Ey, right? But how it is for E theta and E phi, you know? So this is the point. So to know it, to know how to do, to just what to expect. Okay. So to just see the principal plane. So this plane where the field is, where the E field is maximum and linear. So in our case, this plane is called E plane. So an H plane is the opposite one. So in our case, E plane is when what? When phi equal 90. And H plane where phi equals 0. Okay. So if we look, so it depends. So if we look at E theta somewhere like this, right? Because at each moment, at each angle, it is the tangent to this r, right? So this is r and this is theta. And then if this is r, this is theta. If this is r, this is theta, right? It means that, sorry, like if this is theta, this is r, this is E theta. So E theta is going like this based on the angle. It means that at theta equals 0, it is like Ey. At theta equal 90, it is basically easy, right? So I'm expecting at phi equal 90 that E is maximum at theta equals 0, minimum at theta equal 90. Okay, this is good thing. Okay, so to just do it, this is x, this is y. Okay, so what about E phi then? Just draw it again. So E phi, again, it can be like this, or like this, or like this. Means that at, it depends on the plane, okay? So means that at phi, and this is phi, okay, like this or like this. So at phi equal 0, like this plane, E theta equal Ey, this is equal maximum. And at phi equal at phi equal 90, E phi equal EX equal min. Okay, means that the planes where I look at, so I look at E theta at phi equal 90 or E phi at phi equals 0. So it's like I have this case and this case. So here we go then, let's see. So I look at, just see, like E theta at phi equal 90, E phi at phi equal 0. So E theta at phi equal 90, E phi and phi equal 0, right? So we have the maximum and we have just small back lobes and the same for the slot. Okay, so what we can here observe in terms of the both of them is that the slot, it has more back radiation because it is basically having, slot, it can open a little bit something in the back, still small numbers, but this is what we can see. And there is also another observation about the fields generally in the same antenna type, that A theta is going to 0 more than A phi. And the reason is that this component in this plane, exactly, A theta in this plane, it goes to 0 because of the radiation itself, okay? And then it's something like it was 8 shape, and because of the ground, we cancel here, and because of, let's see, okay, so essentially, it is something like I have current over ground, right? This is how the path radiates. So essentially, like I have something like this, if no PEC, and if I have PEC, it will be something like this. Sorry. It will be something like this. And it goes to exactly 0 here, but because of here is not perfect, it is finite, so I start to have some of the H shape. This is what I can see. This is for the E plane. Okay, but for the H plane, it was like this, right? And then I put ground and then cut, right? Cut would be like this. And then I make it finite. I start to have a little bit radiation from the back. So the difference is the shape, or let's say the trend around the zeros, different based on the plane you are looking at and based on the field component. And this is what you can see here, right? And the same for slot. Okay. And then between of the slot and the coaxial, like differences just in the back radiation makes some difference. So what are the other things we can really look at? That we have the cross coupling. Okay. Let's see about the cross components. So first thing is that you can see that for coaxial, phi 0, slot phi 0, the slot has lower cross coupling, and for the other plane as well, this coaxial, This is slot. So the slot, usually the slot fed feeding has less cross polarization between the components, and the reason is if we have the patch here and we have the slot, so it couple, this is the patterns, right? And this is the coupling on the slot. So it does not interfere much with the antenna, does not introduce much asymmetry, means that it just couple with it radiation wise. The pattern itself, like the antenna itself, is not bothered as comparison with coaxial feeding, that I go like this and then I feed like this. Okay, at some case here I introduced piece of metals here. It forces you to have the field itself normal to this, right? Because this is piece of metal, and we know that any piece of metal, any PEC random like this, fields must be normal to the surface. This is the boundary condition of the metal or the PEC, right? So although the field is like this, right, in the antenna, so this disturbance here, it spoils a little bit, but it's not, so big. But as a comparison, the slot fed antenna usually has clean pattern in comparison with the coaxial feeding, or when you use a perturbation in the shape. So that's what we saw here. Okay, this is what we saw here, and you can also see this observation because of here the notch is not exactly on 0, but for the slot it is exactly, because the symmetry of the pattern is more than the other. Yeah, here we go. So this is much of it, like sorry, excuse me for this. So yeah, I mean, I'm trying to see what else we need to see here. Okay, so this is much of it. So yeah, so we can see in the next videos like how this can be different, because for example, if we do an antenna array, the fields accumulate, the patterns accumulate. So if I have an antenna element and then I repeat it, so if I have any cross coupling small, like in dBs, so let's say minus 30 dB or something, okay, and then I have here many elements, and it depends on the phase in between the elements in this side. For example, the summation of, if this is the coupling, and then you start to, it is very small, you start to add in phase, it can finally be big, right? And that's why the cross polarization generally is the most important in the antenna arrays, especially if you have dual pole antenna or something. That's why I was interested to show both, and to show like when you choose this and when you choose this in terms of radiation pattern and back radiation. So if you clean the cross pole, you have to be careful of the back radiation because of the slot, right? And then this can be solved by, if you have the patch, I have here the feeding, and then here's the feeding. So we cover it by PC, and then we shield here around by bias. So we eliminate the back radiation, and then we have everything here. So these solutions we can go through it later. So in the next videos, generally, I'll build an antenna array, and like actual, with the stack up of multi-layers and feeding and doing the matching network and characterizing the antenna performance and showing how to do fast simulations on MATLAB, how to do some tricks, So the main goal of what I'm doing is not like going so deep and analytical things, unless you want, or I see any comments or something. Otherwise, just interesting to show some tricks and to make your life easier. Yeah, so thank you for watching.